So one of the things we are going to be talking about a lot and using a lot is the Heaviside operator. And Heaviside operator is not actually a very fancy thing. It's defined as a derivative. So when you say p of a certain function, f of t, you're really defining the derivative, right? df dt. So this is basically by definition that. And when you talk about 1 over p of f of t, you're defining as the integral, the definite integral from negative infinity to t of f of t dt. So we saw that you can actually use this for defining capacitors and inductors, right? So for example, if you have a capacitor, we saw that we know in a capacitor the current I of t is in an LTI capacitor is C dV dt, so which we could write as C P of V, or in a more compact form, C P V. Or similarly, when you had an inductor, so this is capacitor, an inductor. In an inductor, for example, we know that V of t is L di dt, which you can write as Lp of I, or LPI for short. Now, the operator is applied from the left to right, so you have to be careful about that order. Something like that. Now, you can think about this as the whole thing, as an operator. So you can think about this as a scaled operator and say, this is the operator that takes a voltage and generates a current. Right? It takes a voltage function, V of t, and produces a current. And this is an operator that takes a current function, a function of time, and produces a voltage. So these are basically, for example, we call these kind of operators in general an operator that relates the voltage, it takes a current of a branch and produces its voltage, an impedance operator. So in general, you could write as Z of P, an operator operating on I. So it's really this. The shorthand, what I just wrote was a shorthand for that, producing V of t. This is called an impedance operator. And it's a generalized form of a resistor, if you think about it. Because if you just have a resistor, this operator is going to be a scalar function, right? If you have a resistor with a current and voltage I and V, this operator is going to be simply a scalar, a constant R. Right? So impedances are generalized forms of resistors. When you have different functionalities, when you have things, so you can think about it as a generalized resistor. And similarly, you can define an admittance operator, which relates a voltage to a current. So we show those with Y of P that operate on a voltage and produce a current. And these are called admittances. Operator. And hence the name Y matrix. You remember we had Y matrix, which had conductances before, but now you'll see our Y matrices. We'll do more Y matrices, but when you have inductors and capacitors, we'll have the operator P inside them. So they will become functions of operators. So because if you have inductors and capacitors, you can't just write constances. So these are generalized forms of conductances. Admittances are generalized conductances, and impedances are generalized resistors. Right? But everything is happening in time domain right now. You have a time domain function. This operator operates on it. It generates another time domain function. Nothing fancy about that. So we could actually kind of like, I can just do a couple examples for you to get a little bit of dexterity, gain dexterity with these things. And say one more thing that's important. So one thing that's important is that is our P operator and 1 over P operator truly inverse operators? What does it mean for them to be inverse operators? Means that if they are, go ahead. How? Correct. They cancel each other, but how? If they're applied.
One on something and then the other
Exactly. They're applied in succession. If you applied one and then you applied the other one, you should get back the same thing. Is that true? Well, it is true. So in other words, the question is P operating on 1 over P of a function equal to 1 over P operating on P of the function equal to the function? Right? This is the condition we need to have. We show that P being the differentiation and 1 over P being the integration from negative infinity to T indeed do satisfy this with one condition. F of negative infinity should be 0. Because of the limitation of integration, that constant of integration, etc., etc. Right? The limits of integration. So if you have this condition, then this is true. You can easily verify that. So that becomes a useful thing, because now you can start saying that. That's why I was kind of like, at least one of the reasons, I haven't completely proven this, and we will get there. But that's one of the reasons I was pretty nonchalant about dropping the brackets, right? You can start seeing, because if I have P operating on I, and then I have 1 over P operating on that, I'm starting to think about this as a product. You haven't proven that yet. You haven't really shown it under all cases, all circumstances. But that's the direction we are going. And the point of this operator is that it can turn a differential equation into an algebraic problem in general. That's what it will do. We'll see how it does it over the next couple of lectures. So it's a very powerful tool. It converts differential equations to algebraic problems, which are much easier to solve. So let me just do 2 quick examples before we wrap this up. So let's say I want to see what is the P of cosine of 4t u of t. Let's say this. What is this function? What is P of cosine of 4t times u of t? Let's say differentiation of this, right? The derivative of this. So what is the derivative? So the derivative of the first times the second one plus the derivative of the second time. So what is the derivative of the cosine of 4t? Negative 4 sine of 4t times u of t plus cosine of 4t delta of t. Can you simplify this a little bit more? Can we simplify the second term? What is the second term? Do I need to know do I care about the value of this function at any other time other than t equals 0? No. So what is this value at t equals 0? 1. So this is identically equal to negative 4 sine of 4t u of t plus delta of t. You should get comfortable with this operation. When you have a delta, you can get rid of most of the things that happen in front of it. It simplifies things a lot. Because no matter what else happens at other times other than t, those things don't matter, essentially. Anything that happens at any other time. Unless they're infinities and things of that. So then you have to worry about 0 times infinities and things of that. But for a finite function like that, it just completely simplifies it. It trivializes a lot of things, actually, for you. And that's the beauty of it. That's the strength of it. Now, and then, let's say, one last example. 1 over p of cosine of, let's say, or sine, let's do this, sine of 5t u of t. What is that? How do we calculate this? Think about it. It's really what it is, it's the integral, right? From negative infinity to t of sine of 5t u of t dt. But do I care about this from negative infinity to 0? Why? Because this is 0 for negative times. So what it really is equal to is the integral from 0 to t of sine of 5t prime. Now do I care about u of t? No, it's going to be 1 for this range. So I can completely drop it, dt prime, which is an easy integral to calculate. What is this integral? 1/5 of minus cosine of 5t, evaluated from 0 to t. At t, it is what it is, and at 0, it's 1, so, or 1/5, rather. 1/5 times 1 minus cosine of 5t. So that's what it is. You need to get comfortable with doing integrals that have impulses and steps and things of that sort in them, and so derivatives of that nature. And we'll do a fair number of these to get that going. Yes? Absolutely right. Actually, this result is incorrect, the way I wrote it. Thank you. Thank you very much. Actually, don't forget the u of t. My result, the way I wrote it, was incorrect. Because the u of t has to be there, because I started with a function that was one-sided. And without the u of t, I would have gotten a two-sided result. Thank you very much. Any other comments or questions? No more comments or questions? Very good. All right. See you next time.